Try.
Yeah, I'm just ready whenever. Yeah.
Yeah, maybe we can start now.
Oh,
So
okay.
yeah, let me introduce you. So today we have Soo-hyung Park from the Hebrew University of Jerusalem, and she's going to talk to us about signature zero toric varieties, wall crossings, and cross polytope-like structures. So yeah, thank you.
Great. So thanks for having me. So supposedly this is algebraic geometry, but I'm going to talk about combinatorics. So to start off, there's a common invariant that comes up in a bunch of different contexts, one of which is permutation descent. So if you have a permutation, a descent is this, something going down like this, so an order reversal. But the positivity or like of the same invariant also comes up in signatures of toric varieties, and also things about Euler characteristics of like non-positively curved manifolds of some kind. So here we mean like piecewise Euclidean, so coming from certain kinds of cubical complexes where locally the structure looks like something from a simplicial sphere. And this thing here that gives you like a sort of sectional curvature gives you a signature of a toric variety. This is just for like cultural reasons. I'm not actually going to discuss the third part in depth, but it contains some combinatorial information that's relevant. Okay, so for some combinatorial language of simplicial complexes, an F vector just records a number of simplices, or what I'm going to call faces of each dimension. And the H vector gives you equivalent information. That's why an invertible linear transformation, but it's like more natural for like a lot of algebraic properties. For example, the Hilbert series of certain ring associated to a simplicial complex that we start with. An example of F vector just gives you binary coefficients if you have a simplex, but in our particular context, we'll think about the Betti numbers of the like some toric variety associated to a simplicial fan with the degrees doubled. Okay, so for this local information I mentioned, what I really mean is the link. So like just stuff attached to a particular face. And the star also includes the things that include that face. So to distinguish between the two, um, here you can see that the entire simplicial complex is in purple, and then the link of this vertex is the stuff surrounding it that's attached to it, but not the vertex itself. But the star also includes um, things that have the vertex inside, but this is excluded in both cases. In some sources, the star may be defined differently as actually containing the thing, but this is actually a simplicial complex, so we'll just keep that there. Okay, so going back to the example at the beginning about like the permutation of sense and descents, they are actually related to some natural examples. So more specifically, they have to do with the type A Coxeter complex. So just graphically, you can just like imagine a simplex or just like a triangle, and you take the barycentric subdivision. So you just look at which side of each edge you're on, and just repeatedly subdivide the edges. And if you look at the typical like picture of like a type A root system and like tilt your head of it, you realize they're the same thing. And this actually happens in higher dimensions. And then if you look at the toric variety associated to a particular fan and think about like subdivisions as blowups, you think of a projective space from a simplex and then keep blowing stuff up. And another example comes from cross polytopes. So cross polytopes, I just mean like repeated suspension. So like you have like a pair of points and then you end up with like a square boundary of an octahedron and so on. Like all these things are hollow. And then also here the associated toric variety is a self product of like P1s. Just as just to end, like a key thing we'll discuss here is like some sense of minimality with respect to some like restricted class of blowups. Okay, so a combinatorial property that occurs in like all the examples we mentioned at the very beginning and also the ones we just listed is something called flagness. So a simplicial complex is flag if you like take any subset of the vertex set and you can check if it's a face using the edges. So by edges, I just mean two element subsets. So if you have like the shapes listed here, do you have any volunteers? Like, are some of these like flag, not flag? Like note that like I'm not filling in any of those spaces. Like these are all hollow objects. This one, this one.
I get so the triangle is not flag, but the square is flag for the first
Yeah,
two. Is that
great.
okay?
Yeah, good job. Yes. Yeah, so similar thing
I
also
think
happens.
enough for the 3D one.
Pardon?
Sorry, so I don't know for the other the other examples.
Oh,
I
okay.
haven't thought
I
fast enough.
mean, I think you got the main idea. So like for any simplex, actually the same thing happens because you have every single edge, but you're not the entire vertex that's not a face. Um, and this sort of like square pattern thingy, like kind of occurs repeatedly. So this is like flag, but this isn't because if you look at the middle here, it's not filled in. And a um sort of counterpart of flagness in our particular setting of toric varieties, we'll look at something called being locally convex. So if you look at the cones containing a particular rate, like the union of those cones is convex. And this has to do with like Nef, like certain divisors being like Nef and like globally generated and so on.
Yeah,
So
sorry. I
yes,
think I'm pretty lost. So can you
yes.
slow down a bit and maybe explain to me what G means? What is G in the
Oh,
definition of flag?
that's fine. Yeah, G is just a subset of the vertex set, and you're just asking if it forms a simplex or face or whatever you call it. And flag just means that you can check if this is the case by looking at things pairwise. Um, but then the thing is, if this is hollow, let's look at the first example. Each of the lines, they belong to the simplicial complex, but then we're not filling in the middle. So that's not good because this doesn't belong to it, but then yet all the edges do.
But you said G is like a subset of the vertex set. So what does it mean for the edges? What are the edges of G?
Oh, I just mean like, okay, so to check if a subset of the vertex set belongs to the simplicial complex, it's enough to check if like the edges on it are there. So I mean the things that are already connected by a line. So this does not count as an edge, like the diagonals.
I think that I think here
Is
the
it better?
definition of like G, we're thinking G can be a subset of vertices, but it's also this simplex spanned by the vertices. So the edges of G are pairs, just pairs of any points in G. I think is that
Okay. Yeah, I mean, I think it's a little, okay, if it's confusing, I think it's just easier to look at the picture and compare the triangle with the square. So this is like not flag and this is flag because like this pair is not connected. It doesn't belong to the simplicial complex. But so this like triple, it doesn't belong there either. But then here, all these are there, but this is not filled in. I don't know. Does that help clarify things, or are there any further questions? I'm happy to answer.
Yeah, thank you. Yeah,
Oh,
that's fine.
okay. Yeah, I think that notation might be a bit confusing, but if you just look at these two examples, I think hopefully that can clear things up. Okay, so just to go on with examples, generalizing the thing that gives you the descents, any barocentric subdivision is actually flag, and in particular boundaries of simplices are not flag. And the boundary of any cross polytope is flag. So like repeated suspensions and like taking the boundary part, not including the inside. And the reason we included the stuff with the cubes at the beginning was because the condition for that having non-positive curvature in that setting is exactly like flagness. And the non-negativity of like the alternating alternating H vector or something is like the Euler characteristic that we want to look at. Okay, so in all these examples, including both the permutation and this like curvature thing, the quantity we're interested in is this alternating sum of the components of the H vector. And this is like, to put it in a more general combinatorial context, is the top component of something called the gamma vector, which is like sort of another invariant transformation of the H polynomial. So just think about like Poincare polynomials, I guess. And the non-negativity of the coefficients, it lies somewhere between like unimodality and real rootedness. So non-negativity would imply like the numbers, unimodality means like the numbers go up and then down, or they just stay the same the entire time. And real rootedness is exactly what you think it is. And it turns out that given the recursive properties of the objects we're working with, being equal to 0, like the equality case is like minimality with respect to a certain class of blowups. And the reason is that if you take any flex simplicial spheres, they're connected by a sequence of edge subdivisions and contractions that preserve the Flag property. So translating in terms of toric varieties, they're like blowups and blowdowns, preserving local convexity. So I mean, if you think about the usual like star-stellar subdivisions inducing a blowup, it's just that, but just specifically looking at just two-dimensional cones. Okay, so the reason why we think that zero, like the equality to 0 case is like minimal in some sense, is that if you subdivide the size of that like signed alternating something gets bigger if everything has expected signs. So what we're using here is that if delta is a Flag sphere, the link over any edge is also a Flag sphere, and if it has the expected signs, then the edge subdivision, which we denote by delta prime, has the same sign as the original thing, but it's just at least as large. So this is just exactly what we said. Right, so when the alternating sum is equal to 0, then we expect the size of this thing to be minimal. And what we mean is like, because we talked about this in terms of like sizes, we can also, and according to whether we're subdividing or contracting, we're expecting these things to be minimal, as in like with respect to blowups. So what do these like minimal examples look like? Well, there is some like local information we know, for example, being able to like cover the one skeleton of the simplicial complex by 4 cycles. So by 4 cycles, I mean, I do mean like a literal square, but also like you don't want opposite like vertices to be connected by a diagonal. But it's not really clear how to produce them, and like somehow even in the toric variety case, it doesn't really seem like this has been studied. And I think it is worth looking at because like even for the class of more general class of simplicial spheres, there are a lot of like algebraic structures that are inherited sort of from what you see in toric varieties. For example, like if you look at the like Charring or chromology and whatever in our setting, there is a component that depends on that basically records what the faces are, or like the monomial supported on the faces, and then the rational equivalence relation. And then there's also a counterpart of this for in the simplicial field world. So in the particular toric variety setting, it is known that the alternating H vector sum has that sign. So to what the signature is like is exactly the alternating sum. And so just as a recap, the signature is the signature of the following pairing, the intersection pairing. And here, just note that we're looking at like things that are of like even complex dimensions. So real dimension is like multiple of 4. And the combinatorial motivation for that work was that was about basically how to characterize F vectors of like simple d-dimensional polytopes. So here simple just means that if you take a vertex, there are like d facets meeting there. So for example, consider a cube. You have a vertex and you have like 3 facets meeting there. And the cones of the normal fan forming like a simplicial complex, having a simplicial fan, it's like a dual property. And just using combinatorial methods, you can show that indeed if you take the toric variety associated to this particular simplicial fan with the simplicial complex structure of the cones given by delta, then you have this identity. Okay, so continuing this, just remember earlier we mentioned, oh, the reason for a condition on the fan aside from being simplicial is like some positivity condition on the divisors. So you're like, okay, maybe this is some stuff about intersection numbers, what's going on? Yes, that is indeed the case, but it did take some work. So the first step is, okay, I have a bunch of words, but I'll actually say what this means. We have an alternating sum, but we want to show it's non-negative. So first we want to show it's a sum of reasonable looking things, namely certain Euler characteristics, which is what like the first step does. And then the second step says, oh, okay, this is a product of like each term that we're adding is a product of some characteristic classes. So there's some hope of turning these into nice intersection numbers. And the second step is, okay, well, thanks to the signature theorem and like just using the splitting principle as usual and pretending we have a set of line bundles, we can decompose this into like understandable parts that look fairly combinatorial. And the stuff about conormal bundles and conormal bundle restrictions, that is like restricting, say, like, for example, a ray divisor d rho to like the restriction of ray divisor d rho to d rho. I mean, like the single I over I squared. And restrictions of like, say, some ray divisor to the same ray divisor intersected with like more ray divisors, right? That's what I mean by conormal bundle restriction. Those things come in because of the residue maps. And then turning this into a reasonable looking collection of intersection numbers comes from like functoriality properties involving Chern classes. So the upshot is that after doing all this, we end up with a strictly positive linear combination of some intersection numbers that are non-negative. So because all of these are strictly positive, we need all these intersection numbers to be 0. So when p equals 1, we literally get this, and then what we meant by conormal bundle restriction is what we said earlier. Okay, so just as a short note, like while these are even exponents, we're actually gonna focus on like when a bunch of like intersection numbers or equivalently mixed volumes, if you go to the polytope world with odd tuple exponents, they all go to 0. Like assuming of course they're of top degree. And because they're surely positive, we need all these to be 0. Okay, so what's going on here? We have a bunch of identities, like how do we actually think about this? Okay, so are there any questions so far? Okay, if not, then I guess I'll go on. So
If I ask
So-
something,
Yeah.
sorry, about the previous slide for this,
Yeah.
like the last, could you remind me what the notation, like sigma, the notation sigma means, like the lowercase
it's the same
sigma?
signature.
Okay, like the alternating sum of the HIs?
Yeah.
Okay. I see. Okay, thanks.
Yeah. Any other questions?
Next slide.
Okay.
My question is exactly the one. What does this mean for the fan? So
Oh, yay. Okay, that is the entire point of the talk. Because so far there has been a lot of interesting work. Like, okay, given some properties of fan or simplicial complex or whatever, can we show non-negativity? And then how about like the converse? So because of the earlier work, we know this like recursive relation, but what is like this sort of like base structure? Okay, so we'll take this like step by step. So because we have these like positivity properties of the divisors, we have mixed volumes of polytopes, which will turn to a combinatorial thing. But the actual interesting thing about using the conormal bundles and the restrictions in particular is that because these are basically like the mixed volumes of polytopes, you can think of as taking sums of the polytopes. I'm going to actually go over definitions here, but the point is if you take points of the polytopes and see if the spans are like large enough or not, do they take up the entire ambient space? And if you take the orthogonal complements to these and you can also interpret them in terms of like how the links over the cones are realized in lifts to different spaces. So if we just took a look at the p equals 1 case, this is a link over array lifted to the ambient space of the entire fan. And you're asking if there are any positive dimensional linear subspaces contained in that. And this correspondence makes sense because they're polar duals to each other. Because the vertices of the divisor polytope of like an F divisor correspond to the normal vectors to the facets of the graph of the support function of that divisor. And then interpreting this like latter thing in the second bullet, in terms of these realizations comes from looking at the base divisor expansions of these divisors. So this is also in that previous work, but it doesn't seem like they pursue these like this further. So okay, what do I mean by like this like mixed volume stuff? So first we need to start by defining like Minkowski sums of polytopes. I mean, it's exactly what you think when you say, oh, I'm adding stuff together and just add the points to their respective parts. So just like a baby example is if you have two triangles, you can like put them together and just translate one by things in the other, and you get a hexagon. And in general, if you can sort of like decompose this in terms of like sums of the individual faces that, like as you can see in the dotted lines, and you see hints of this in what we mean by mixed volume later on. And aside from this, the divisor polytopes behave nicely with respect to Minkowski sums when the divisors are enough, but in general, we only have containments. All right, so now on to mixed volumes. So one way of looking at this is like volumes of like Minkowski sums of scalings of some initial set of polytopes. Another point of view is, well, okay, it's a mixed volume. So presumably if everything's the same, you'll just get the volume, which is true. Also, it has some nice properties like multilinearity, and the order of the weight, like the order you consider the polytope shouldn't matter. Yeah, so going back to our picture, one way of thinking about the mixed volumes is like if you take a Minkowski sum of like the polytopes, and look at the multiplicities AI is assigned to each polytope QI. Like remember how like the faces induce like a subdivision? You look at the sort of tiles that come from faces of the dimensions like AI. But the formal point of view is also like important because like if any of the polytopes is a point, you actually get 0 by like multilinearity. I mean, this is also consistent with the like divisor polytope thing, because if you just have something that's linearly equivalent to 0 to divisor polytope's a point, and the intersection number should be 0 if like one of those things is 0, so that makes sense. And this is just the correspondence that we're making use of for NEP/globally generated divisors. Okay, so back to our actual setting. So these are the things that we said should vanish. And equivalently, we just rewrite this in terms of divisor polytopes. Okay, so what's actually going on? So let's like look at p equals 1. And in that case, what happens is that, sorry, wait, can everyone see the picture, or do you like see this weird bar thing? Do you see the cursor?
Yeah, the picture is showing up, I think.
Oh, yeah.
There's like two sides to the two diagrams.
Yeah.
Example
Okay.
1 and 2. Yeah.
Yeah. So there are two parts to the example. I know I said I'm looking at the even, but I'm sorry, I don't know how to visualize 4 dimensions because I don't have superpowers. But yeah, so basically this is saying like yeah, so if this is like if the conormal bundle is like yeah, so basically you're saying like there are two different ways things like this could happen. Either it's literally flat or something like this. Okay. So if we have like higher dimensional like cones that we're taking links over, there are some choices that we can make about what we live to, but like how do we understand these? So yeah, so let's take a look at this. Yeah, so I think in the other picture I like did not label the ambient variety, but the point is that of course, just multiplying stuff together, you can see that one's a stronger condition than the other. But what it means is that if you assign like if you look at the usual ambient space for a link, which is like quotienting stuff out, you assign a height 0 to one, like not 0 to the other. So there are things that can be completely flat in the ambient space of the entire fan, or that might not necessarily be true, but when you quotient the right stuff out, it is. Another thing you can imagine is like you have like I don't know, you have like I'm not sure what you call it. You have a V and you're like stretching it out like this. So from one direction, things are flat, and the other side it isn't. Okay, so to actually figure out like some structural properties, we're also going to look at these conormal bundle restrictions from like a Cartier divisor point of view, which we can do because it's like simplicial and we can just multiply by a positive constant, do whatever. Right, so just in general, if you're looking at the orthogonal complements of these like divisor polytopes, which we're doing because we want to understand like if the spans of the Minkowski sums of the polytopes are big enough, and if they're not, then how badly does it fail? And it's just the intersection of like spans of walls satisfying these properties. And you can sort of guess this from looking at the vertices of the divisor polytope, because if let's say some alpha, let's ignore the underlying things first, is orthogonal to like any line between the vertices, and it's like orthogonal to the entire thing, and that's equivalent to being orthogonal to PD. And because you can traverse through all the Maxwell cones through wall crossings, you can actually restrict to those Maxwell cones sharing a wall. And if you take a look at this intersection number, this looks similar. And because our fan is simplicial, we have a basis expansion of the ambient space of the fan using the rays of any particular Maxwell cone. We'll just choose this one. And because if you take the inner product of this piece of Cartier data and like the ray divisor, the rays essentially, and just you get the ray divisor coefficients again. So you can't ignore the terms that come from the wall, and that's why you end up with this. Okay, so before moving on to
Sorry, could I ask
Yeah.
a question
Of
about
course.
this? Sorry if I missed this earlier, but by a wall here, does a wall just mean any maximal dimension piece of this, like the D-1 skeleton? Or
I mean, it turns out that yes, you can. Yeah. I mean, if you take a random simplicial complex, you might have weird stuff happening, but just because we have like fan of like associated to a toric very weird. Yeah.
okay, got it, thanks.
Yeah, I mean, okay, just imagine a normal fan of a simple polytope. So everything is going to be reasonable.
Okay, like sigma here should be like that.
Yeah, I mean, in our particular setting, everything's actually going to end up being a normal fan of a simple polytope. A rational polytope in particular.
Okay, thanks.
Any other questions? Okay. All right, so before I move on, we're just gonna go over some notation we're just gonna use repeatedly. So if we index some collection arrays forming a cone by some set, we're gonna just write sigma and elements of that index set. And then for our particular thing, the rays that end up generating the orthogonal complement, we're going to call the special rays, and then the other rays are going to be called non-special because they're not special. And just going back to our stuff about maximal linear subspaces, they're going to be like generated by the special rays. But just as a warning, like unless this like maximal linear subspace is like one-dimensional, like it doesn't necessarily mean that the antipodal point itself is also a ray. It simply means that also lies in the support. Okay, so the main technical tool we're going to use is the following. So basically the orthogonal complement of the divisor polytopes of the conormal bundle restrictions, or any sum of them, is gonna come from vanishing of like certain conormal bundle restrictions. So the first is like is like a further restriction of the conormal bundle showing up in the mixed volumes that or intersection numbers that we want to vanish. And the second one looks a bit weird, but we will explain where it comes from. So before actually explaining the statement, I will go into like what steps we took to get to this thing, which will hopefully explain why this makes sense. So just to visualize what the statement says, if you take okay, so I didn't come up with these pictures, but so I listed a source, but okay, so instead of just viewing the entire thing at once, we're just gonna look at things piece by piece. And this intersection being like 0 basically means it's kind of like flat. So this basically gives you a linear subspace that doesn't intersect alpha. And then for the second property, if this is strictly positive, you get something that kind of looks like this. So, I mean, it looks convex, right? I mean, if this were negative, you would have like the gamma and gamma prime being like behind like the complement or the quotient or whatever you call it. And that would not look convex. Like Pac-Man is not convex, right? Okay, so why do we get like all these things going to 0? Well, if we take a look at the like spans that we're intersecting, because the fan is simplish, so it's like intersecting like the span of whatever like span of intersections. And the stuff we're intersecting is like, let's say we're in a fixed cone simplicial fixed maximal cone sigma, things that give a non-zero product, like intersection product. So if we omit this, we are stuck with the gamma that does this. And so it might seem reasonable that we end up with products of this form or this form where the walls come from removing a special ray from a maximal cone. And because we want this to occur for like any possible wall containing a particular special ray, because we're intersecting all the like spans of all the walls with like that non-zero in like product. Like the fact that if you have like the intersection of some divisor with like any torus invariant curve being 0 implies that the is 0. And applying that to this restriction gives you the second highlighted thing. So that is what we get from the first two steps. And then the third one, that looks kind of odd, I guess, is basically when you traverse through all the maximal cones of your fan, what you end up with is like, okay, the first two steps tell you that you're not going to lose any more rays as you traverse things when the rays stay on the wall. But if it's off the wall, that's the only chance you have to like decrease the dimension. And I'm talking about decreasing dimensions because everything's simplicial. And if we already had the intersection of the entire thing to start with, it would just like persist through the entirety of the wall crossing, the traversing all the maximal cones. So another way of saying that is that if you take the original set of special rays on the first maximal cone that you start with, then it should be equal to like the span of it. Like the replacement should also give you like something like this, where both the boxes are non-zero. I'm not saying the boxes are the same, but there's boxes because I didn't feel like writing letters down. But in any case, if you compare this with the wall relations, it implies that the like certain intersection products are 0. And that is exactly what we get over here. And then applying this to any maximal cone containing a particular non-special ray and the special ray, like basically the same reasoning as going from this to this, gives you the second part of the second bullet here. So essentially what this is saying is that we can describe like the orthogonal complement of the divisor polytope of a conormal bundle restriction in terms of certain conormal bundles, like restrictions like vanishing. I know these look a bit strange, but there will be some combinatorial results to put this in context. Are there any questions? Okay, if not, then I'll just go on to an example that looks less weird. Okay, so hopefully you believe that if you take a self product of P1s, the conormal bundles will be 0. And we also get a cross polytope because we have like a bunch of like antipodal arrays going like this. But what about the other direction? So this is like when we actually start relating this to the combinatorics of the fan. And it turns out that if you assume the fan is complete, the converse does hold. So we'll go over some of the reasoning. Okay, let's like first fix a single ray of the fan. Then what happens is that because the restriction of the conormal bundle, like the conormal bundle itself is a 0, going through this polar dual stuff basically says the realization of the link in the ambient space of the entire fan is a codimension 1 vector subset. So it's a hyperplane. And because it's an actual hyperplane and not like, I don't know, bent up like this or something, like the cones of the fan, that the maximal cones of the fan that contain rho, they actually take up the entire upper half plane on the same side of this hyperplane as rho. And what that means is like you can't have any other rays there on that side. So for the remaining rays of the fan, you split into 2 cases, like whether the hyperplane, like the support of the link of that fan is equal to that of rho or whether it isn't. And if it isn't, then, well, the hyperplane has to contain something on the same side as rho, but it has to be rho itself because of the stuff that we just explained. Now, if it is equal, then, well, alpha is not equal to rho, then it has to be on the other side. And the same reasoning also implies that alpha is the only thing on the other side. And repeating this for all the rays on the link of rho, because, well, every ray, because of the first analysis in the first case is either rho or something in the link of rho, we end up with just a bunch of suspensions, at least combinatorially. And in this particular case, you can actually use induction on dimension to go even further and say that, yes, we do end up with a bunch of like antipodal points forming rays. And that's just kind of using induction on inside the hyper intersecting like 2 of these different supports. But I'm not going to get into it because we're not going to use it in further arguments. But the upshot is that the vanishing of conormal bundles conversely implies like we have a bunch of suspensions. And actually, even on a conormal bundle restriction, we have a pretty big constraint on like adjacency properties. So what we mean is that if we can replace the center like of the conormal bundle restriction that vanishes by some other ray, you don't have a lot of choices. So it's either like in this like link over J1 all the way to JM without omitting JR already, or it's on the other side of that hyperplane inside like this quotient in ambient space. So, okay, so what does this mean? So here we just looked at this conormal bundle and the conormal bundles and their restrictions in the abstract. But if we take another look at the this sort of structural result, it forces a lot of things to be attached to each other by suspensions. Well, okay, we'll break whatever I just said into parts now. So if we fix a particular special array of rho, that is the something in the orthogonal complement of the divisor polytope of the coronal bundle associated to rho, then all but one possible ray beta, such that gamma is a special ray of beta, is actually like adjacent to rho. So actually everything we have a cone or a repeated suspension of one. And for number 2, if we start with a particular like non-special ray of like a specific ray rho, then you have a similar situation with the possible non-special rays. I mean, the thing to note here is that unlike part 1, we actually lost the dependence on gamma. So that kind of means that like the entire link is formed by like taking this like linear subspace and like suspending a bunch of things over it, specific rays over it. So for part 1, I just like drew a picture. So, okay, so the general idea, which I can't actually draw because it just gets too complicated, is that just imagine a cross polytope, except that you replace the rays by like cones, because what one really is about is basically suspending a bunch of like cones over like a linear subspace. Here, what this picture says is just simply like 2 adjacent rays that, and by adjacent I just mean like forming a cone of the fan, that happen to share a special ray. So like this is the line that lies in the realizations of both lengths. And here, the point of like this picture for part 2 is that the things that are attached to a particular like linear subspace, when we look within a particular cone and not like in between cones like part 1, is that the suspensions are more like in a combinatorial sense, like they're attached to all but one thing, but they don't actually have to be antipodal, unlike the cross polytope case, which is why we kind of avoided saying that in the conormal bundle restrictions. And you can see that here because like if you quotient out by rho, of course you would like end up with something flat. But here we just have something like this, and then the rest of the non-special rays would like be attached to both of these, I guess. Yeah, so this just gives you some idea of local picture, and then actually, even if we save for this for a single like row, like basically you can say the same thing, replacing row with a higher dimensional cone. Like in particular, going back to the span intersection stuff, like we're going to intersect a smaller collection of walls, which means something bigger. And because we already had like all these like monomials vanishing, like any ray is the link over any cone contains a special ray for that particular ray. And so this for an even less restricted condition, we end up with some kind of cover. So this corollary is kind of more of the same, but the point is that because we have that the signature is 0, these kind of funny suspensions like over linear subspaces by like cones covers the entire space. So this is also saying things backwards because we want to first say how we're going to construct the link over each ray. And then basically it's a linear subspace suspended by a common collection of rays. And then going the other direction, this is about suspending the cones. By cone, I mean like the link over a particular array, and here we're suspending the centers of the individual cones. So it's like flipping perspectives, like from the perspective of the stuff that you're pulling over. And here, we're just saying a bit about like what it means for like comparing to let's say we are looking at like a 2-cone or something. Basically we're looking at if certain arrays have like a common like special array or not, like common line in the realization of links. Okay, so the point is that because of this like condition that all these things vanish, the individual links are suspensions over linear subspaces, and the way these links fit around an individual, if we look at any of these like linear subspaces anchoring the entire thing, the way the links fit around also form a suspension. So it's kind of like a weird thinking of a cross polytope that's like stretched out by linear subspaces. And again, we can just restate all of this for P cones. Are there any questions? Okay, so we have some idea of the general shape, but like, so we gave like a lot of restrictions on like what the possible general shapes can be. But we've only made use of the identity from P equals 1. Like, what about the other ones? So as it turns out, we can say that this has something to do with maximal linear subspaces of like link realizations, the things that we're suspending around and like how they intersect. Just as a note, like in order for these mixed volumes to or intersection numbers to induce non-trivial conditions, we need the arrays involved to be like mutually non-special, because our earlier result about all these like vanishing conormal bundle restrictions actually just kind of automatically implies a bunch of monomials vanish. So before getting into this part, which is like more combinatorial, we'll try looking at mixed volumes again. So remember how we said essentially we're looking at whether a Minkowski sum of polytopes has like a sufficiently large dimension? It's a sort of thing about like linear dependence type properties of the spans in some sense. And note that again, because of like multilinearity stuff, this implicitly assumes each of these polytopes has a dimension of greater than 1. And this is actually pretty relevant to like our setting, because we shouldn't forget about the triviality of the divisors that we're working with. That kind of actually happens a lot. Just most notably the cross polytope. So Minkowski sums of polytopes have a simple definition. Like you just add stuff together, right? So fine, if you're given a particular collection of polytopes, then maybe it's not so hard to understand. But if you're like, oh, like what do these things look like as a whole? That's a lot less clear. And in particular, when you try to actually like work with this, all you have is like, oh, maybe the intersection like contains things that have common indices and so on. You know what? It's just easier to add numbers. Let's just like add numbers instead. So instead, we'll focus on the exponents. So equivalently, the sums of the exponents coming from like how many times you use each polytope in the mixed volume is less than or equal to the Minkowski sum. Like in order, so these are equivalent conditions for having non-zero mixed volume, okay? So focusing on these exponents, we will call like such inequalities the non-zero mixed volume inequalities. And the collection of exponents like satisfying these properties as a non-zero mixed volume region. Okay, so just as a remark, like in our setting, we will take these to line d minus p because well, we're taking the intersection of d array divisors in a d-dimensional toric variety. And it turns out that, okay, maybe if you're familiar with some of the combinatorics, you might see that this kind of looks like the defining inequalities of like a generalized permutohedron, and indeed you do get one. I mean, just like for permutohedra, you can think of like the points 1, 2, 3, 2, 3, 1, and so on, and you just take the convex hull after permuting all these. And in a small case, you get nice things like hexagons and anything beyond this, beyond my drawing capabilities. But in any case, you do get actual permutohedra if these are like maximally linearly independent. Like the spans, of each polytope, they're just, yeah. So our question about all these monomials vanishing when the signature is 0, it basically boils down to when are there no odd tuples in the non-zero mixed volume region? And yes, permuted are pretty, but there's an actual reason I'm mentioning these. And that's because the conditions under which like these non-zero mixed volume regions, like these points fail to exist, they have to do with like certain inequalities that define such shapes. Okay, so now let's actually look at an example. So as you might expect, this is a weird property. So what I mean is that usually you would expect an odd pair to exist unless something weird happens. And here, A1 and A2 are exponents. So first we have like the non-zero mixed volume region. And then we like slice it with quote unquote hyperplane, which is just a line because we're in 2D. And usually you end up with enough points here so that you can just pigeonhole an odd pair, assuming the correct like parity conditions. But if this thing is like a actual corner of a rectangle and not just like a truncated one, then you actually need parity conditions. So yeah, essentially out of edge cases, we expect an odd pair to exist. And the thing is, we want to somehow make use of this for generalizations. And just looking at the exponent point of view on these non-zero mixed volumes will define the Minkowski sum of some initial collection of polytopes with dimension BA if we look at the sum of the polytopes indexed by elements of A. And we'll also define omega A to be the orthogonal complement of this polytope. Okay, so again, we have d minus 2 because of such and such setting. And here, the thing that we actually lift to is like dependent on the conormal bundle restriction that we're considering. To be more specific, it's this. And that's because we start off with the space where we quotient out every single ray here. And then we actually assign like heights for the ones that are indexed by A, so they're no longer quotiented out. I know that like this makes an implicit choice of linear subspace inside the ambient space of the entire fan, but it turns out the choice doesn't matter. Okay, so it turns out that what we see in P equals 2 does occur in other cases, and they have something to do with these inequalities called the submodularity inequalities. They're exactly the inequalities that are needed to say that inequalities with like A1 plus blah 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 is less or equal to some number. Like the inequalities these numbers need to satisfy in order to be permuted are exactly the submodularity inequalities. Okay, so let's take a closer look at something that helps with a more general picture. So the P equals 3 case is similar, so we won't get into that. But the submodularity inequality itself is defined as follows. I guess the usual version here, we can think about in terms of like, if you take the Minkowski sum of like polytopes, then the dimension of the intersection is greater than or equal to the dimension of like the sum of the polytopes over the common index set, but then you might have more intersections. And that's why you might end up subtracting more than you expected, hence you would have this inequality. But something that is more useful for generalizations and maybe a little bit conceptual is a specialization, which is kind of like a rate of marginal increase in some sense. So if you add in an element K, how much of an increase in dimension do you have? If the thing you started with is smaller versus like thing you started with is larger. And that's another way of thinking about this, which will come up later. In any case, when we specialize, like this is for like Minkowski sums of like whatever polytopes. If we actually plug in the divisor polytopes that we started with, what these give us are linear dependence relations between the linear subspaces, the maximum linear subspaces, and realizations of lengths. So I understand that might be complicated, but the sort of the general form of the linear dependencies we get are like P is a Minkowski sum of polytopes and Q is a Minkowski sum of a subcollection. So like because Q is smaller, the orthogonal complement's like it contains it because like Q itself is contained in P, and R is like a new polytope. And if you just rearrange like the stuff in part one, it's not hard to see how you get this. So okay, so another specialization here is okay, either we have this trivial situation locally, so like you have partially things that are partially stretched out and partially like bent in like a convex way. Or you have something like the situation in part two, where these two arrays, which are adjacent to each other, they share a common special array like this. So we note that like the collection of like rays that can be associated to a particular line or like special array, they're pretty special, so they're cone-like or like just a suspension, a bunch of suspensions. We know that in this particular case, the parity of the like exponents doesn't actually matter. Like if this happens, then all the top degree, like namely degree d minus 2 monomials in these two conormal bundle restrictions actually end up vanishing. Yeah, what's happening here? This is like basically the third case we mentioned with like the box and like the corner. So if we're in the quote unquote generic setting where the realization of this link doesn't contain any possible dimensional linear subspaces, when in this case of the entire fan, then we have this kind of inequality, and at least one of these two is even. So I tried to draw a picture here. I understand like the dimensions too low again, but like I cannot draw things in 4 dimensions. But the point is that you might have things that individually have like linear subspace containments, but then the axes are different. They're not a common linear subspace. Like you might have a linear subspace containing a realization of the link over one ray, but not for the other one. Another thing to note, which we'll actually mention in the generalization of this, is that what this means is that like the one ray is always like non-special with respect to the other, so we have like a bunch of suspensions. So these are just the pictures zoomed in. So it turns out that like this sort of like analysis we did for like the links over like two cones, you can say very similar things about links over p cones. Like this is again the trivial case, and this one you have a more complicated version of the picture in part two. And then for part three, actually it kind of explains the situation in part three more clearly. Aside from the parity conditions that need to be satisfied, which we did not list, the fact that every single array here is non-special with respect to some rho ij means that you're forced to have a bunch of repeated suspensions because the set of possible non-special arrays associated to a particular starting ray like is formed by a bunch of repeated suspensions. Okay, so going to the other end of the p between 1 and d minus 2, though you can one in some sense the most degenerate case is like p equals d over 2. You can sort of already guess this from just looking at the monomial because like the thing is 0 and the exponents are all like only 2. You don't have any big exponents. And in addition, like what it means for this like thing to be equal to 0 means that like you fail a condition you need to satisfy for any odd tuples to exist in the non-zero mixed volume region. Okay, so the third point starts off with stuff that is relevant to any like collection of polytopes, and then we'll specialize a bit later in the same point. So suppose that at some point we failed to satisfy the inequality. We either started with something completely trivial, or we have this being satisfied until at some point this happens. So there is a transition point. And when we specialize the polytopes that we start with to the conormal bundle restrictions, what happens is that when we look at like some chain of inclusions of like index sets, then we end up with an inclusion of maximal linear subspaces in the lift of the same link to different spaces. So essentially what we mean is that previously with the sum modularity stuff, it was like a linear dependence and there's a containment. But the thing is that the word transition point here is a bit weird because like hypothetically we could have things that induce like this condition to fail because 1, 2, 3, but then we can catch up later. Okay, so we claim that somehow in higher P, like things between 2 and d over 2, the behavior lies somewhere in between these. So for p equals 3, it turns out like almost the exact same thing happens to p equals 2, so we won't discuss it, but we will say a little bit about the general case, which is kind of strange, but not totally unexpected. So so this is like starting off with like, okay, you want to find an odd tuple in a non-zero mixed volume region. So let's say you have some, you have like an n-1 coordinate thing that does satisfy it, and you want to add a new coordinate that still preserves a non-zero mixed volume property with respect to this like new set where you add this new index point. And if you add the minimal possible like element, it does indeed work. And basically, this sort of like silly method actually gives you a vertex of the generalized permutation, the polytope formed by a non-zero mixed volume region. So you can think of this as like take some linear form, and there's a unique minimum at this particular point. Because of the special properties of the like Minkowski sums of polytopes, that actually gives you a vertex. So because we want a tuple, what if we like force some modifications, right? Just add one or subtract one, whatever you need to. I mean, intuitively, if odd tuples exist in a non-zero mixed volume region, like there must be something optimal, right? Like there are finally many things to check. So what would such points failing to respect non-zero mixed volume inequalities mean, right? Like it's not hard to make small changes to force like all the coordinates to be odd. Well, we're not going to state the full answer because it's kind of long, but the point is that the differences of the sum modular, like of the two sides of the sum modularity inequality, so like the rates of like marginal increase are small compared to the number of index sets, like producing this like p equals d over 2 kind of behavior. So like these kind of linear subspace containments and like certain parity condition on the dimensions. So basically we're saying that like we're not very far from the kind of linear dependence that is like induced by like equality cases of modularity inequalities. So it's a little complicated, but it gives a kind of idea of like what information do the other monomials tell us. So to finish off, we'll go back to a theme that we sort of discussed at the beginning of the talk. So what was known about the structure of these like sort of minimal Planck spheres was that they're covered by four cycles. But both the proof that you have this like blow up, blow down type thing from edge subdivision contractions and this 4-cycle stuff, it was kind of like a existence proof, so it wasn't really clear how you would produce these things. And what I mean by induced 4 cycles, just to clarify, is like, okay, you look at the one skeleton of the simplicial complex, and you end up with like a square, and the diagonals are not in the simplicial complex. Okay, so yeah, so in particular, concrete examples were not very well understood. So turns out that using wall crossings gives you a way to generate these. And the funny thing is that in a lot of combinatorial contexts, like for example, what are possible normal fans of things that of like polytopes with a certain property, for example, being a generalized polyhedron, you make use of the wall relations which come from intersecting rational equivalence relations with like a one-dimensional orbit closure. But here we're going to make use of like two-dimensional orbit closures. Yeah, so our main tool is the following. So if you have a simplicial locally convex, complete locally convex fan, this sort of intersection being 0, means that alpha is contained in an induced force cycle. So essentially it is kind of like, there are a lot of arguments that are similar to the main like wall crossing lemma we had earlier, like after the span intersection, but the key input of the conditions listed at the beginning are basically from like the diagonals, not the convexity and the flagness imply that the diagonals don't actually like form cones of the fan. And the way we produce a like fourth like ray to consider, or a fourth vertex in the simplicial complex language, is to multiply a rational equivalence relation by this two-dimensional orbit closure. So like we quotient out the wall by this rate alpha. And because, you know, this is 0, we actually have like an extremal rate here, right? So putting all that together forces a force cycle to exist. And if you put this together with like the initial structural condition that we mentioned, like immediately after the span intersection thing, because each ray is adjacent to some special ray, you always have like some relation of this form for any ray alpha or like rho in the context of the simplicial fan. So we can cover everything with the induced force cycle. So yeah, and it turns out that apart from this, like the same rays induce the sort of flat wall crossing property for both like alpha and its opposite ray. Okay, I think that's all that I want to say today. Thank you.
Yeah, thank you for the talk. Are there any questions or comments?
So I have a few questions. I mean, one, I'm just trying to put the results sort of into context. I mean, so are these sort of specialized results about toric varieties or toric realizations of other sort of classification results that we know in more general context, if that sort of makes sense?
Well, it depends on how you think about it. So I guess like there are certain like in a more general context, in the context of flake spheres, it's known that you have these edge subdivision and contractions, and you have like suspensions to construct these flake spheres, but I don't think there were any like global results beyond like very specific computations and very specific examples. The reason we're focusing on toric varieties, aside from like them not being studied, is that the simplicial sphere case, they also have like a counterpart of the Chowring, with the sort of storing the Stanley-Reisner ring information, and also like some counterpart of rational equivalence.
Good. Yeah. So that was going to be my sort of follow-up question. So I guess, so what's happening in the Stanley-Reisner Chow ring? I mean, you're getting sort of relations of
Yeah,
some
you have something
forms.
like a regular sequence called a linear system of parameters. Except it's basically like how the points lie in space, except you replace the rational equivalence relation by some other collection of things that reduce the dimension, like return this into a finite dimensional thing. The things you're allowed to choose depend on the particular circumstances, but yeah, there are a bunch of things you can do there.
So that's sort of, so in particular, I mean, that's not going to be true for many toric varieties, but for these special toric varieties with the signature 0 sort of structure, you're getting structure in the Chow ring that's sort of particular to that. That's what you're.
Yeah, of course. So I think this is the sort of apart from the explicit results, I think the point is more like you have certain positivity properties of like, let's say a Poincare polynomial, or like with the double degrees or half degrees or whatever. you want to look at what do these combinatorial properties imply about the underlying fan structure. I think that's kind of really the sort of meta thing here.
And so maybe as a final question, so there's no way to sort of relate this to, say, the signature of like the anti-canonical class, like the sort of Chern matrix or whatever.
I haven't tried. I mean, it seems plausible, but I haven't really thought about it. That's a good question.
Yeah, okay, thanks.
Okay, are there any more questions?
I had a question about this. I think you drew some diagram or example about the odd point condition. I think it was slide 38 or 39, and I was wondering if I could
Are you
ask.
talking about the weird rectangle thingy?
Yeah, I think there are like two cases, like one generic, yeah, this mixed volume region and odd, the odd tuples. Do you mind explaining again, like how the diagrams correspond to like the
Yeah,
odd tuple
sure.
condition?
Yeah, I like did not actually say how these are proved. It's just a pigeonhole thing. So, like, you look at where like these you split into cases about where like you're starting where you would enter and exit the non-zero mixed volume region, assuming that you lie on the particular line. And then you just say, oh, because you have enough points, you will get an odd pair at some point. Just because you assume that like the dimension over here has even parity. So if you have at least two possible things available, then one of them must be odd.
Okay, I see.
Yeah, that was it.
That's the space. Okay, got it. Thanks. And then and then the second case involves some for like more technical argument. Is that or
I mean, the second case is literally like you don't have any other points in the intersection. I mean, okay, it's not so much like a more technical argument, but like, if in order to get this like non-zero mixed volume thing, you need C to be less than or equal to this. And if like, and because like, if C is equal to this thing, because this like, you already assume that C is less than or equal to this, it has to be less than or equal to this in the first place. It has to be, these two have to be equal. And like within such a region, like that's only possible if each of the coordinates attain their maximal values. Like C is like basic, what I mean is that C is the sum of the two coordinates. And like this is like the value you would get if you add the maximal value of each coordinate. Is that, maybe that's more intuitive? Because like, if you make either of those smaller, the sum's gonna be too small.
okay, yeah, okay, I think that makes sense. Maybe if I like go look at the slides for more context. Yeah,
Okay,
thanks.
that's fine.
Any more questions? If not, then let's thank Xu-Hyung again. Yeah, thank you for the talk.
you.
Have a nice day.
Okay.
Yeah, bye.
Bye.